Having seen how the cluster breaks its data down into ranges, replicates and distributes those ranges to the various nodes, and uses the Raft protocol to keep cluster data durable and consistent, we're now going to look at how those nodes act together to keep data available in the face of node failure. Consider a 3-node cluster, the smallest size for a resilient production deployment, and let's connect a client. Whichever node the client connects to is called the gateway, and it'll route queries wherever they belong. This is something we've been hinting at, but now's a good time to make it explicit. The client can make any node its gateway just by connecting. Next, note that the leaders of the various ranges are not all on the same node. They're distributed roughly equally among the 3 nodes. Suppose that a client sends a query asking for rows from 2 of those ranges. Here's how the query might get answered while 3 nodes are up. First, the gateway would route the query to the appropriate leaseholders, and since it's a read query, they would send their results back to the gateway, which would combine them and answer the client's query. The only difference for a write is that there would be a consensus operation started by the leader for each Raft group, but the flow would otherwise be similar, with an acknowledgement returned by the leaseholder back to the gateway and onto the client. In a production cluster, there would be potentially many clients connected to each node, all doing this in parallel. Okay, so what happens when a node goes down? Well, first, if a client is connected to that client would need to find a new gateway. This problem would be solved by using a load balancer, which is crucial in production deployments. More interesting, though, is what happens to those ranges in the moments immediately following node failure. Suppose a write comes in just as a node goes down. If the leader is on a node that's still up, there's no problem. But for a range whose leader went down, there's a short-term problem. No leader. That Raft group will hold an election, turning a follower into a new leader in a matter of seconds. The lease will be reassigned as well, and the gateway will route the write to the new leaseholder. Once it knows that the remaining 2 nodes have achieved consensus, it'll acknowledge the write back to the gateway. So the cluster is able to keep serving writes as well as reads with perhaps a few seconds of latency, but only if the query comes in at exactly the wrong time and it touches on a range that's temporarily leaderless. That said, we are down to 2 nodes at this point, and until that node comes back up, while the cluster is able to serve reads and writes just fine, it's also in a fragile state. If the second node is lost at this point, consensus becomes impossible, and the cluster will be unavailable until it's back to at least 2 nodes. We'll want to get back to a resilient state as quickly as we can. When that 3rd node does come back up, it'll rejoin the cluster and, assuming it hasn't been too long, its ranges will rejoin their respective Raft groups as followers, replicating Raft entries, and the cluster will again be in a resilient state. Okay, so what have we covered? Well, we've learned how the gateway node works, we've seen how a 3-node cluster responds to maintain availability in the face of node failure, and we've seen how it recovers resiliency when the lost node reconnects.